Hi, everybody. Welcome to our webinar. People are still joining us, so let's give some time and we will play a short video, 1.5 minutes, and then we'll get right back.
Effluent, safe and compliant air filtration process is essential for efficient industrial manufacturing processes. Challenges to overcome are often related to explosion safety, health work environment, emission legislation, energy reduction and recovery, and improving economics with effective extraction of dust, vapour, odours and aerosols. At JOA Air Solutions, we innovate air with tailor-made industrial air filtration systems when standardised solutions will not suffice. Our proven process includes a site visit, take measurements and report back our findings. Then we use our in-house developed air technical modelling software to predict future airflows and create a perfect start for our concept design. Based on this blueprint, we build new or updated systems, on time and commissioned the first time right. After commissioning, we will provide onboarding, regular preventative maintenance and spare parts to keep your operations running. In over 22 years, we have advised over 100 manufacturers from the food, pharma and chemical industries with tailor-made solutions and implemented over 2,000 air filtration systems worldwide. This will result in you getting back control on your operations with a balanced solution fitted to your product, process and requirements. With JOA, you are guaranteed to have the best future-proof solution for your site.
So, welcome everybody again. So, thank you for joining us on in this webinar. So, let me start the presentation. So, what's this webinar all about? It's about waste heat recovery for industrial processes. Please use our chat function if you have any questions. My name is Bas van der Boog and I'm here with my colleague Martin Turker, who will also take you into our technologies. So, again, please use our chat function. The aim is to spend 30 minutes on this webinar. So let's start. Again, what's this all about? Specifically, we address today low and medium grade industrial waste heat recovery. What's that? That's everything between 60 and 300 degrees. And why? If I see at the attendance list, we have quite some experience also on the higher temperatures, so 300 plus degrees. So where we still have a huge potential to gain for the next coming years, it's the lower temperatures. So as I said, everything between 60 and 300 degrees, average is around 120 and 300 degrees. So that's what we're addressing today. And what's the potential then? Well, the potential is huge. We used the data provided by the EU, and of all the energy used, 26% is used within the industry. And only 51% of that energy use is useful, is used right. And out of the 49% wasted, it's 29% involved in exhaust and effluents. So that's the target. And to give you a ballpark figure, the potential there is 126 terawatts per hour. And that's equivalent to 20,000 3 megawatt windmills. So again, the potential is huge. So what's then specifically where to focus on? Well, the biggest potential there is in the chemical and petrochemical industry. Iron and steel, non-metallic materials, paper, pulp and print, and food and tobacco. So this is, well, quite the potential also for our clients and all of you attending, which are often represented in these industries. And what you see here at the right is then the amount of lower temperature and medium temperatures used in that exhaust energy. So there you see, for example, in the chemical and petrochemical industry, that the potential for low and medium waste heat it's used. It's almost, well, fully used there. And it's the same for in the food and the tobacco. Almost 70% is a medium and lower temperature waste heat. So that's where we're focusing on, and that's where potential is. We use Carnot as an indicator. And what this slide gives you is, okay, how we calculate the potential and how easy it is to recover. And Martin will address more on this later on, but this is what we use to really investigate the potential and how easy it is for lower and medium temperature waste heat. Now, okay, so this is where the focus on. But now, how we do it? Let me give the word to my colleague Martin Turker to dive in to that topic.
Thank you very much, Bas, for your introduction and the clear indication that there is a lot of low and medium grade waste heat potential to be recovered. The question is, how do we do it? And an important question there is, how do we integrate this heat? So the first thing to look at is to really determine at your sites, at your plants, from the individual sources, the potential. And then we are looking both at the sensible and latent heat. Because other than, for example, Carnot is the latent heat, and very important parameter here. You might have drying applications where you have large exhaust streams with a temperature of, for example, 80 or 100 degrees C, and there is quite some energy loss there. However, there might also be that one stream with a rather low flow, for example, 5,000 cubic meter per hour. However, with a very high moisture content, which has a lot of potential too, if we would make use of the condensation of that heat. For example, if you have a dew point of 95 degrees C, you can gain a lot of energy from that. And one of the examples is given here at the right side. It's an ERD scrubber, which is really taking out the latent heat from the exhaust stream. However, as we're talking about industrial applications, there are always pollution risks and corrosion risks. So it's very important to really understand the process and what measures have to be taken to prevent for pollution, or, for example, to apply in situ cleaning to make sure that the heat exchangers first of all are not affecting the process, but secondly are also running reliable and for long periods. We have, for example, heat exchangers which are automatically cleaning every day or every second week, depending on the application. And then the last very important topic is to identify the potential consumers. Ideally, we are working with the closed loop. So let's say the energy source will also be the consumer. So if you, for example, have a dryer with an exhaust stream, we might be able to return the recovered heat directly into the dryer and really giving an energy reduction for that process. That's ideal. However, not in every process possible. And then we will be looking broader. For example, how can we utilize this heat for your utilities, for example, or can it, for example, be applied for cooling purposes? So we really have to first understand what's happening in the sites, in the plants and within your processes, and from that we are looking how can we integrate that heat, because recovery is one, but the integration, especially with low potential heat, is often the largest challenge here. So we are using a waste heat management here, and at the left side you see the waste heat, the sources, and then we are first looking what kind of processes are we talking about. Are those, for example, batch process or continuous processes? If you're talking about batch processes, storage might be a good solution. In other cases, recovery is the right solution. And from there, we will be looking into the integration Do we, for example, have to upgrade the heat, so increase the temperature before we can apply it, or can we, for example, use it for a neighboring process? Today, we will not look into all the different solutions here, but we will be focusing on three main ones, which are, well, which we think are interesting to look into more detail when we are talking about the low and medium potential waste heat. Those are the industrial heat pump, the absorption heat transformer, and the absorption heat transformer. However, as already mentioned, this is not the complete thing, of course. Also, often solutions like twin coil solutions are applied, where heat is recovered at one source and it's conveyed, for example, via water or another media to the air handling units and used to preheat air. Those kind of solutions are, of course, also available, but today we have limited ourselves to three technologies. The first one is the industrial heat pump, and it's within the industry already used for many years. The heat pumps and mechanical energy is used to compress the gas, and due to that, upgrade the heat. Another interesting one is an absorption heat transformer, and what is done here, certain components of the air are subtracted on the absorbent, for example, the moisture, and then the air can be reused again in the same process. And as a benefit, the absorption process is also exotherm, so it's also directly increasing the temperature. And the last one is the absorption heat transformer or absorption cooling. Within absorption heat transformer, basically the same is done like with an industrial heat pump. The temperature gets a certain lift. However, the process behind it is chemical. The absorption cooling is used if you would like to utilize the waste heat for cooling purposes. So the waste heat of, for example, 80 degrees C, 85 degrees C can be used to generate chilled water of 6 to 12 degrees C. And typically, this is not the first thing to think of in your processes when you're looking into waste heat, because, well, we're talking about heat. But it might be very interesting to explore this this opportunity, especially if you are using process cooling. So the industrial heat pump, how do we apply this? Nowadays, more and more high temperature heat pumps become available. And if we are talking about drying processes, we are getting, for example, recovery streams of 85 degrees, 85 degrees Celsius. And this heat can be used to generate low pressure steam. And many processes in the industry are driven by steam. Let's say the heat, the thermal energy input is by steam. And in many cases, the steam pressures in the plant are, for example, 8 or 10 bars. However, if you're literally looking down into the processes itself, 2 or 3 bars might already be sufficient to operate the process. And if we could then make a closed loop with the recovery and the heat pump, which is from the waste heat, upgrading the heat to low pressure steam, it can be a very interesting solution to make a closed loop from the recovery to the consumer. So the industrial heat pumps are interesting in this field. The only thing which has to be added here is electrical power. So to give you an idea, if you're looking from output, about 1/3 of the energy to be added is electricity. and the rest is driven by the waste heat. The second technology is the absorption heat transformer, and in many drying processes this can be very interesting, because what happens is the exhaust air is partly let through the absorber, and if I say partly, this can, for example, be 80%. So 80% of the exhaust air will be let through the absorber to take out the moisture content, but also certain VOCs. And this is really depending on the process and whether this is a good solution. However, as the air is dried, and in a dryer, this is the main purpose, to start with dry air to take out the moisture from the process. As we are drying the air here, the same air can be recirculated much longer, and we are also getting the exotherm reaction back. So depending on the application, there is also a certain temperature lift involved. So if we are thinking about the low potential heat, and we also see, for example, drying of the air can be an interesting step here, and it really can give you a large savings on the energy input of your process as such. So in our eyes, and very interesting concept which can be applied for many applications in the FMCG industry. And then the last technology to focus on or to explain today is the absorption heat transformer, or the chiller. The technology is more or less the same, and a chemical process is used to generate a temperature lift, or to generate chilled water. So the waste heat again is used as input and given back to the process or to the building utilities at elevated temperatures, and then you can think of in the range of 30 to 50 degrees higher temperatures. The absorption chiller is interesting if we are looking into the process cooling applications. So again, waste heat of typically in the range of 80 degrees C, but of course also higher. However, 80 degrees C is something we see often in our industry as an input parameter at the low side. Can be used. That's more or less, let's say, the lower limit for this kind of technologies. And here we can utilize it for process cooling, or, for example, cooling of the buildings. And those devices are also applied for example, during winter times. They might not be used. And only during summer times, but during winter times, the hot water or the waste heat is used for building heating. So there are different concepts here, and it really depends on your plant what's the best fit. It just gives some examples on how to integrate the low potential heat here. However, how do we get there? Because well, there are, on one side we've got the waste heat, we've got the stacks which are exhausting a lot of energy, as Bas has indicated. About 29% of the industrial energy intake is wasted here. And on the other side we have the consumers, and the integration between is the most complex matter. So how do we get there? And typically we are doing a quick energy screening where our engineers come out and to take measurements and really understand your processes. And during those screenings, we will also be looking into your processes itself to find other maybe optimizations you already can make in your process. Because of course, if you can have a process optimization, that would be the first win and the best to do. Next step would be to look into the exhaust streams and to link them to the user. So we will take measurements and then model the potential. We are using our GCM model there. I will explain it in a minute, a little bit. And from there, the opportunities will be ranked. So the key purpose is, of course, to reduce the energy, but the important step we are making here, how do we integrate it into your plans? And from that, savings and recovery solutions are also given. And the processes we are often focusing on are, for example, your dryers, your ovens, furnaces, incinerators, etc., cooking and frying equipment. Many of those kind of processes have rather high exhaust streams and give good possibilities for recovery. And the tool we are using here to identify and to really calculate the possibilities is the GCM tool. It's our own in-house modeling software to really model your exhaust systems with all parameters involved. So it's not only the capacities and the static pressures and the temperatures, but really all entropies, etc. are here. And it gives you also clear insight to maybe come to the conclusion that you nowadays have a process with 4 main exhaust points connected to it. But if you would take 2 off, the potential for recovery becomes much higher, as we are, for example, changing the dew point of your streams, and use of latent heat can be made. So it's just an example of the modeling tool we have in-house, and we are using always for the energy studies. I hope the explanation of the technologies was clear for you, and I would like to give the word back to Bas.
Thank you, Martin. So we've talked about low and medium temperature waste heat. And I want to conclude this. We want to conclude this and also to have an outlook of what does it mean for you. And of course, it reduces your energy footprint. And especially when we are talking about improving economics of your site or cluster within the company, there also we see a lot of developments on incentives and subsidies available. And also, when we're talking about low and medium temperature waste heat, we also think about, okay, what's the optimal point of the return on investment? We have to be realistic here. There are typically slightly longer return on investments, what we usually see in our projects. But that's, again, the balance between also the economical and installation lifetime of 20 plus years. So again, we see a return on investment times of between 5 to 7 years often, but again, this is really depending on your specific site. So we see a lot of opportunities on improving economics and energy recovery. We see also, of course, that with this recovering of low and medium temperature heat, we see that we are contributing to the greenhouse gases reduction, and often also to your company 2030 goals, and also in line with that, when we're talking about emissions, we're also reducing the carbon taxation and by waste heat recovery. So this is to summarize what kind of benefits we see when we are dealing with this topic. And we see also some big developments still to come, especially when dealing with low medium temperature waste heat. So we, with JOA and also with our research partner TU Delft, really investing time and money into the absorptive technologies. And the solution we see here is heat amplifying. And how do we do that? That's by chemical heat pumps. So we invite everybody, especially our current partners, or potentially future partners, to join us into this in this journey of several years to really investigate and also look into the revenues of adsorption by heat amplifying. So please reach out on this topic if you would like to join us. So we still have time for some questions. So let me do so. So first question was from Theo. So Martin, especially in the topic discussed. So Theo asked, how do you recover or convert waste heat from a process that has a large variety of hydrocarbons and also a wide variety of flow rates?
Well, thank you, Theo, for raising the question. It really depends on the application, to be honest with you, because if we are talking about the large variety, storage of the heat might be the best solution, because we have to integrate the heat somehow. And then if we would store this heat, it really depends also on the application. But if we would store the heat, it can be used on the moment you need it. So if you're really thinking about the large fluctuations and kind of beds of operation, storage could be a very useful method to make use out of it. But it really, we would have to look into more detail also what kind of VOCs are involved, of course. But this can be addressed, of course.
Thank you. Well, we have received several questions. Hakan is it okay? Are you also considering emission limits? Yes, we will surely do so when we investigate and especially model. We often talk about our holistic approach in projects and challenges, the way we work in our consultancy approach. So yes, we will for sure look into the emission limits. Of course, safety, as Martin said in the beginning of his speech, that we look into the fouling streams and how does it affect the recovery. So yes, this is all taken into account. Well, we have still time. Oh, Mohammed has a nice question. Thank you, Mohammed. How do we recover heat from high moisture? Well, Martin, this one is yours. This is
Okay.
your name all over it.
Thank you, Mohammed. Recovery with high moisture is very interesting, because what, for example, can be done is have a scrubbing application. It depends on the temperature, but what we will be trying to do is make use out of the condensation, and because it will give you a lot of energy. So we will be scrubbing your stream with a very special scrubber, which is able to work with the condensation effect, and from there the heat is transferred to a user. So an example here would be the ERD scrubber, as shown on the slide in the beginning. That could be one of the solutions without knowing anything more from your process.
Thank you. So we have received more questions. We don't have the time for it now, but we will address one more. But if you raise your questions, we will surely come back to you individually and also share with all the registrants and attendants in order that everybody is up to date. Question, do you have any plan for high-grade heat recovery in the future? Yes, of course. Maybe my voiceover in the beginning was not that clear, but we have a lot of experience on this topic. And well, to be really black and white on this is the easy part compared to low and medium. And again, when I see the registrant and attendee list, I think there's a lot of experience also in the room here. So yes, we will continue to do that type of solutions. But again, the future on waste heat is also addressing the lower and medium temperatures. Let's see. Let's take the last one. How much, Martin? More on the low grade absorption chiller you addressed in the middle of the presentation. how much is the COP of low-grade absorption chiller in this application?
It's in the range of 0.7 to 0.8. That's the typical COP we are seeing with an absorption chiller. 0.7 to 0.8.
Okay, thank you. So, well, it's time. Thank you so much for attending. We really enjoyed it, and we will surely share the replay. We will share the questions raised and answers given. If we could not address your question, we will surely do so afterwards. Again, please reach out if you want to know more about energy recovery or about our research and development initiatives. And let's talk. Have a great day, and thank you so much for your time.